Okay, this video is for AP Calculus. We're talking about the disk method for volumes of solids revolution, washer method if there's a hole in the rectangle. And we covered all the main ideas in the first part of this video, but we're going to do additional examples, 3 additional examples in this second part. Let's just take a look. So we'll always start by sketching what's going on here. Let's do that. Let's see, if I graph this, y equals x squared. So let's see. Maybe not too far here. Okay, y equals x squared would go like this. Y equals x squared. X equals y squared. Really, it goes over here as well. X equals y squared would be this. And the reason I'm only graphing that much of it is because I can see that this is the enclosed region. And then we are rotating that around the line x equals negative 1. So let me change colors here. X equals negative 1 would be this line. That's the axis of rotation. And that means we're going to put our rectangle on here. Disk method, perpendicular. It grows from the axis of rotation until it covers the material here. So something like that. Looks like we have to go through a hole before we get to this, and this is in the y direction, so it's a dy type integral. Right? And then that means we have 2 radiuses, 2 radii. There is a small r that goes just to the edge of the hole, and then there's a larger r that goes all the way to the edge of the rectangle. Okay, so let's look at the larger r first. What establishes the larger r is this boundary here, which is y equals x squared. That's a 2. Okay? And that is a distance in y, and that means that this distance here is x squared. But to that, we also have to add this on, because the radius starts from here and goes there. This distance is always 1, so this capital R is going to be x squared plus an additional 1. Okay? Except, wait a second. I was assuming that this is a y. Back up. We have to make a change here. This distance here is a distance in x, which means I have to take this boundary curve, which is y equals x squared, and change it into x as the square root of y, so that I can write this in terms of y. I can also see that my width here is in the y direction, so I'm going to have to only have y's in here. So this distance here is x is the square root of y. This distance here is always 1, so this radius is square root of y plus 1. There we go. Now we've got the right variable. And similarly, this r here, this little r, is established by this curve, which is x is y squared. So this little part here would be y squared, but we have to add the 1 onto that. So the little y is going to be the little r is going to be y squared plus 1. And then I can now make my volumes. I've got 2 integrals here. So from a to b of pi big R squared dh minus the whole, which is pi little r squared dh to make a washer. And so this is going to be the big R, we said, is the square root of y plus 1, and that has to be square root of pi r squared dy. And then we'll subtract out an integral pi little r squared, which is y squared plus 1 squared dy. And then we have to integrate this from the starting and ending y values. So these are pretty clearly intersecting at 0, 0, and 1, 1. So the y values would be y equals 0 to y equals 1. This would be 0, that would be 1. And if you do math 9, you get 3.037. If you have these reversed, if you somehow have something reversed, you'll end up with a negative area. It's likely that the answer is just the negative of that area, but there's other mistakes that can happen. Okay, as always, you can pause these problems and try them on your own before you unpause and see the solution. Got two more examples for you. This says set up but do not evaluate an integral for the volume of the solid obtained by rotating the region about the specified line. So whenever a problem says that, you do have to show the setup, but you're not required to do either the hand integration or the math line to get the answer. So let's go ahead and draw the sketch of what's going on here. Let's see, y equals -2, I see. So we're going from 0 to pi, and it's sine. So I know that sine has that kind of shape. It goes from -1 to 1, right? And it completes one complete cycle from 0 to pi. So if I have the line y equals 0, which is the x-axis, and that curve, we're talking about this part of the sine function. Okay, but then they want us to rotate this around -2. So let's draw that in here. The axis of rotation is supposed to be y equals -2, which means we're rotating this way. So there'll be a big gap here, and then there'll be another copy here when we rotate this around, right? It's a giant shape like that. It's, I've got a shape like that. So it's kind of a weird, like, bowl with a big hole chunked out in the middle of it. All right, so we're going to go ahead and put the rectangle on there. The rectangle grows from the axis of rotation perpendicular to the axis of rotation, so it has to go upward. And we're heading towards the original area. There's a hole, and there's some stuff filled in. This is in the x direction, so this is a dx type. We've got two radii. There is little r that goes to the hole, and there's big R. Radiuses always grow from the axis of rotation outward. Well, this little r to me looks like it is always just 2. For the whole thing, it's just 2. But this r here consists of this, which is the y for the curve. And the curve is y as sine x. So this would be sine x, plus there's also a fixed distance of 2. So this big R is the sine x height plus 2. Right? Okay, so let's go ahead and build this. This is Washer method, so an integral from a to b of pi big R squared dh, and then subtract out the whole pi little r squared dh. This is going to be pi, the big R is sine of x plus 2 squared, and this is a dx type, minus an integral pi little r squared, which is 2 squared dx, and we're integrating at x's. So we're starting at x is 0 and ending when we get to pi. 0 to pi, 0 to pi. This said setup only, so this itself is the answer. Okay, I want to show you one thing too. So I really like doing two separate integrals, but a lot of times answers in backs of books and things will be like this. They will simplify this integral. So let me show you the correct way to simplify it and the incorrect way to simplify it. In green, I'll show you the correct way. So a correct simplification would be if you took the pi out of both of these, wrote it as one integral, and did sine of x plus 2 squared, the whole r squared, and then subtract the little r squared, and then have dx. This is okay. But what sometimes people will do is this, and this is incorrect. The reason why I don't do the one integral right off the bat is people will mistakenly do this. They'll see sine of x plus 2 minus 2, and then they'll square that. Okay? That is not the same. Okay? Because if you square something minus square something, it's not the same thing as these two things subtracted first and then squared. So this is incorrect. Make sure you don't make that mistake. One way to not make the mistake is just to always use two integrals. That's really the best. It prevents the mistakes. All right, one more example. I think that's it for this lesson. So one more. Let's do a graph of what's happening here. We have, looks like y is -3, so let me make this more like this. 2, 3, 1, 2, 3, 4. There's a line y equals 4. Y equals x squared, which could be 2 squared is 4. This is the 0.24 here. And the y-axis. So it's that area. Rotating around the line y equals -3. Okay, so if this is the axis of rotation, and that means there would be 1, 2, 3, and then there would be another shape down here. So you've got this kind of hockey puck looking thing, and this rotates around. All right, you're not required to do the 3D part of the sketch. Depends on your teacher, but for me, I require that students always do the 2-dimensional sketch and show the rectangle. That's the minimum sketch that is required for a full credit of my class. All right, so perpendicular, we're going to talk about the rectangle going from the axis of rotation until it covers the original area, or something like that. This is filled in. This is a opening in the X type, so it's a dx. We've got our 2 radii, a little r, and the big R. Looks to me like the big R is established by this, so that is just always a fixed distance of 4 up here and a fixed distance of 3 down here. So I think R is simply 7 though. Okay, the little r is a little more complicated. It consists of this, which is a y, and it's established by this boundary, which is y is x squared, so that is x squared there. But then it also has this distance, which is always 3. So the little r is x squared plus 3 more. Now that I've got my capital R and my little r, I can fill that into the formula. Pi big R squared dh minus integral pi little r squared dh. So the big R is always 7. That's an R. The big R is 7, so that's 7 squared, and this is a dx type. Integral pi little r, that's going to be x squared plus 3 squared, don't forget to square it, dx, and then we have to integrate an x, so that's going to be from x is 0 to x is 2, as we're using x values. And this one didn't say otherwise, so we'll evaluate it. It becomes, by math 9, 180.956. If there were units, it would be 3 units. All right, and that's it for shell/wash or disc/washer method. There is another video, next one, which covers a second way to solve this, called the shell method. That's applicable only to AP Calc BC. However, although we include it because it's part of Calculus 2 with analytic geometry and the course curriculum for Rio Salato and for most college courses, the shell method has never appeared on an AP exam. So all the volume problems that you encounter on an AP exam for Calc AB or BC will be solvable with disc or washer method. So this is the main method.